Hi, and thank you, Kenji. So I just said I'm Sebastian Merle. I work for the company Peer Stritzinger, a company well known for GRISP, the prototyping hardware for running Erlang bare metal. The presentation will be an introduction to software-defined networking and traffic engineering, and the work that is going on in the European research group TeraFlow. So first, I'll be introducing what is software-defined networking, SDN for short. So let's take a simplistic network service provider infrastructure as an example. It is composed by multiple routers. They are all linked together. And let's assume that they are all configured and they know how to route packets between them. So some of the routers are entry point and exit point to the network, and we will be calling them head-ends routers. We will focus on the use case of setting up a tunnel between two of these head-ends routers to let packets flow across the network area. This is what we'll be calling flows from now on. So traditionally, configuring a flow is a manual process. A network administrator would connect to the routers with SSH, for example, and configure them using a vendor's command line interface. A step up from this is the use of netconf, configuration protocol. Netconf strives to make the configuration format more standard between vendors. And another big advantage of netconf is its support for transaction. This is so if you have configurations that involve change on multiple network elements of your infrastructure, you are sure that the configuration is changed either on all of them or on neither of them. Very important. So, but there's still issues. Even so netconf made configuration more standard, there's still format discrepancies between vendors. There is no central knowledge about the flows you're configuring. The administrators have to keep track of them on their own, and it usually involved lots of scripting, specific administration software and such. So software-defined networking is about delegating all the vendor abstraction and the flow management to an external service called the SDN controller. The service provides a standard API, so the administrator can set up flows and keep track of them, and all the flows are stored and managed by the SDN controller that communicate with all the network elements independently of which vendors actually provide the interface. So this is for the very quick overview of what is a SDN, and I will try to do the same now with traffic engineering. So first, why actually do we need traffic engineering? So in a network, all the links are not the same. You have links that have a lot more bandwidth than others. You have links that have lower latency. And you may have even links that actually cost you money to use, real money, and you just want to use them sparingly and really case by case. So a SDN controller without traffic engineering rely on the underlying network to route the packets between the head-ends routers. So this means that all the flows passing through the same head-ends router usually follows the exact same path in the network. Usually the shortest path. This is depending on the actual routing protocol underlying. So because of that, the SDN cannot really take advantage of the full capacity of the network. Some link may not see traffic, and while others get overloaded, and this would prevent us to create new flows. So with traffic engineering, the SDN learns the topology from the network and constantly keep it up to date in a database that is rightfully called traffic engineering database, or TED for short. So with this knowledge, the SDN controller is able to set up each flows to follow a specific path by calculating, taking into account all the possible constraints that are available at this time. So the SDN will keep track of all the links you have in your infrastructure, the usage, how much flows are passing through each links, and this way is actually able to distribute all the load of the flows on the networks without links getting overloaded or underused. So, and given this knowledge, the SDN can even migrate a flow from one path to another path at any time. This is a really useful function. For example, if you have a very low latency link in your network and you have a few flows, you want to use this low latency link because low latency is always good. But at some point, the administrator may request a setup for a new path that actually require low latency. And you don't have any space anymore in your low latency links. So the SDN will just take one of the flows that is there, migrate it to a path that has higher latency, but given it's not a requirement for this path, this is not a problem, and free up space for the new paths that have more stringent requirements. Another important aspect of traffic engineering is the ability to set up a flow passing through multiple network areas. This is done by cooperating. The different SDN will cooperate with each other, and each of them, knowing the topology of their own network, are able to stitch a path between that would pass through all this network area. And this is only possible to do in an efficient way if you actually know the topology of all these networks. So now I wanted to give a bit more detail about the protocols involved in traffic engineering. To learn the topology, the controller can simply take part in the inner gateway protocol called IGP for short. It could be iSize or SPF, and this is the protocol that the underlying routers use to discover each other's and to know how to route packets between each other's. Another common protocol uses BGPLS. BGPLS is an extension to the border gateway protocol is specifically extended to carry topology information. This is a kind of an abuse of the protocol to transmit link state information. This is why it's called BGPLS for link state. So to configure the flow, the SDN could use either PSEP, that is a path computation element protocol. This is a standard protocol designed for traffic engineering. And another option is to use OpenFlow. OpenFlow is a bit special in that it's when your SDN is able to take over the control plane of your routers. To very quick detail on that, a router is composed of two things: the data plane, that is what is an extremely fast layer that is able to move packet around between interfaces, and a control plane that is controlling this and filling up this routing table, forwarding tables on the router. This is usually called like the brain and the muscle of the routers. And with OpenFlow, if the router allowed it, the SDN is able to take over this control plane and directly control the forwarding table on the routers of your network. So as we're focusing principally on PSEP for now, I'll talk a bit more about it to give us some context. PSEP is the name of the protocol. This is a path computation element protocol. This connect the client part, the PCC, the path computation client, and the server part, the PCE, the path computation element. The PCE connects to the PCE, and in fact, could even connect to multiple PCE. Only one of them will be the master one, and the other one will spare PCE, that in case the main PCE is not reachable anymore, the PCE would switch, elect a new master, and redelegate all its flow to the new master. So there's multiple ways of triggering a path computation. The client, the PCC could itself request a path to the PCE. If a path is configured on the client or something trigger a need for a path on the client, the PCC will just do a computation request, the PCC will calculate it, returns it, and the PCC will use it and possibly delegate it to the PCE. The other option, and the one that we're probably more interested in, it's a proactive creation of a flow. So the PCE, triggered, for example, by the administration requesting a new flow in the network, would contact one of the PCCs that is connected to it and ask and request the PCC to set up a flow. So the PC will set up a flow and then delegate it to the PC. So I'm insisting about this delegation thing because all the flow are actually owned by the PCC and only delegated to the PC, so the PC can then modify it whenever it wants. Okay, so all this talk, and you're probably wondering if there's actually anything working. So as this is a very early stage of a 3-year research program, there is still lots of work to be done, but even so, we already have implemented the PCEP protocol in Erlang and a PCEP server, and this is what I will try to demonstrate now. So I will switch the sharing to my console. Okay. Oh, yep, I went too fast. I went too fast. I wanted to give a bit of more context. Okay. About the setup for now. So for the demonstration, I will set up a virtual network on my desktop on a single machine. Each of the nodes will be running FRR. It's an open source routing software I've been involved with. It will use ISIS as a IGP protocol with segment routing. If you don't know what segment routing is, I'll try to give a very quick explication during the demo. Don't worry too much. So it will use the path daemon. This is a network policy manager daemon I wrote with Sasha, a coworker at Stritzinger. It supports PCEP and will be your PCC in this demonstration. So for the virtualization, we could use Mininet, but as I happen to have been involved in the path daemon, I got used to their internal Mininet-like tool for testing. It's called NetGen, and I'll be using it instead for convenience. This is NetGen. So NetGen is a very simple network virtualization tool that uses Linux PID mount and network namespaces to set up complex network very fast. And finally, I will use the Erlang PC that I've been talking about. So now I'll be really switching to my console. Do you see it? Everything there? So to give a bit more context about what we will be doing, I will show the topology I will be actually using. So this is the topology I will be setting up on my machine. It has a source node and a destination node that I will be actually used for testing the flows. It contains 6 routers. These routers, there's multiple of interconnection between them. There's a switch, there's double links and such. And there's a PCE node that is connected to both heads and routers. And this is where we will be running the Erlang PCE. So this is all running in Ubuntu virtual machine. So this is a virtual network running in a virtual machine. So I will be starting the NetGen. So this is starting all the network elements that we could see in the diagrams with all the FR daemon on each of them. So this gives us a TMX session where we have a session for each of the node that we seen on the topology, and the one with the star is the active one. So now we will start testing. So we want a flow between source and destination. So I will just do a simple ICMP, a simple ping between source and destination. I will ping destination from source, and this will create a flow of ICMP packets in our network. So I'll go to the source node. Yeah, and I will just ping the destination node. So as expected, at least for me, there's no packet flowing between the source and node because I actually didn't start the PC yet. So both the router 1 and router 6 do not actually know to set up a flow between these 2 points. So I will just start it right away. So I go to, and I start the Erlang PC in console mode. So this may take a bit of time to, oh, they connect right away. So there was explanation back off, so I wasn't sure how much it will take. So here you can see that the router 6 connected to the PC. It requested a path from router 6 to router 1, and we responded with a stack of labels. I'll give a bit more detail about what are these labels in a minute. That identifies the flow and the route the packet should take in the network. We see here that router 1 connected to, want to pass from router 1 to router 6, and we responded with this stack of label. So I will quickly talk about this label thing. This is what this is about segment routing. So here you can see that these numbers on all routers are some as what is called labels. This is a way of routing packets in a network where on each packet you prepend a stack of identificator that are these labels that indicate the different point in your network you want the packets to travel through. So this is a bit like if you want to travel to a very far away city, you just need to know like the 2 or 3 big cities on the path to these cities, and all the rest is done by the underlying infrastructure. So this is it. If it's all start with 16, this is because this is a master block. These labels are allocated as blocks, and this is the blocks used by ISIs in this case to allocate this label. So if you didn't understand what I just said, you can just think of it as a way to identify a specific routers, and similar to what could be an IP just saying that, okay, path through these routers. So let's back to the to our network. So now we say that we set up this flow. Like for example, here we see that for 1 to 6 we pass 20, 40, 60. So to 1 to 6 we pass to 20, 40, 60. So this is the path we actually set up. So let's see if actually it's work. Go back to the source node, and we see that we actually the ping are passing through. So now we are actually pinging the source, the destination from the source. So, but let's see that we are supposed to go there. Let's see now where these packets are coming from. So let's go to router 5. And let's see if we are seeing actually this packet. So we use this interface, router 5, this interface, RT3-1. And we just only unpay this packet, so no sign of ping there. Other interface, no sign of ping there. So let's see on router 4. Same thing. The interface is RT2-1. Nothing there. This wasn't because I forgot to filter, so this wasn't wasn't the packet we're interested in. So this is not there. And so we found our ICMP packet. So we know that they pass on router 4 second links. So we know that all the packet and the reply and the request are passing through this link and going to destination and going back. So now let's do some traffic engineering. And we'll do that by actually going to the PC and changing the routes that have been allocated for this flow. So let's go back to the PC. First, at what we actually have configured at this time. So right now we have you have two routes, the 1 to 6 and the 6 to 1, and this is the labels we have. So what we want now is change this label stack. So we'll do this, but this. We update routes. So for the route from 1 to route 6, and we want the request, instead of passing through this part of the network, we want to pass it through the other parts of the network. So we want the label to be 30, 50, 60. So 30, 50, 60. So router 1, which is router 6, 30, 50, 60. So the date and the dedicated route got active. So let's first see if we are still pinging, so the offload packet is still there. And now if we go on router 4, we see that we don't see the request anymore. We only see the ICMP reply. And if we go to router 5, we started viewing the echo request. So now we actually have the request passing through this part of the network and the reply going to the other part of the network. We migrated one half of this bidirectional flow. So just for completeness, we will now move the other part of the flow. Update route. So the route from this time, so from the router 6 to the router 1. And we want for this path to pass to the same other side of the network. So this way, this is 50, 30, 10. So this is 50, 30, 10. Oh, 6 to 1, 50, 30, 10. Up, active. So now if we see, still pinging, router 4, we don't see any more ICMP packet. And router 5, we now see the both request and replies. So this is this demonstration of how we did all this with a PC, Erlang PC, to do traffic engineering in a virtual network. I'll go back to my presentation. Is it done? Okay. So that is for the demo. Now I would like to introduce the research group that is impulsing this work. So TeraFlow is part of Horizon 2020 Research and Innovation Program. It's a 30-month research plan that started in 2021. And as you can see, there's collaborators from all over Europe. It's quite a diverse bunch. First, I'll start to give some context for the goal of the research. So in a world beyond 5G, infrastructure get very complex. There is lots of parties involved. Even though this is already very simplified, this gives a better idea about the different parties that have to be taken into account. So, for example, this is the core network. This is the backbone of internet with all the big core data centers. You have the city network, the metro network. This is the one that is on each city, created on each city, and then you have the radio network. And on each of them, you have processing capabilities. You have so even with 5G, even in the radio network, you can have edge computing with multi-access edge computing devices. So this is the kind of a scenario that TeraFlow want to simplify. A goal of TeraFlow is to design a scalable service to provide a standard API to set up and monitor end-to-end data flows in this complex context. A service that could optimize the management of all these flows, the resource usage, the quality of service, and a service that could handle the huge amount of flow that is required by this post-5G connectivity, where you have a myriad of mobile devices and lots of IoT devices. Like everything's connected, cars, and so everything wants a flow, and everything wants to be connected to at least one of this processing zone. So another aspect of TeraFlow is the standardization of network virtualization called network slicing. This is about providing a real shard of network infrastructure to customers, to tenants, and allow them to the freedom of configuring them, managing them how they wish. This could be used by the network provider to scale the number of customers without modifying the infrastructure, for example, or by customer to set up isolated network for low latency 5G application. So this is, so to summarize these research lines for TeraFlow, it's about researching and defining a set of open standards for API and automated configuration and management of all the networking flow and the independence from multiple vendors. So creating this API for this side too. It's about network slicing and network virtualization for scalability. And a big part of it, and the one that we are most involved with, is the design of a service that could scale for the requirement of these post-5G networks. Another research line is the inclusion of machine learning for threat analysis and threat detection. So this is all good, but what about Erlang? So as I already showed, we already have something working in Erlang, but as this part of this project, or part of TeraFlow, there will be two of these controllers that will be implemented. One based on traditional microservices in architecture and containers, and another one based on Erlang and OTP. So this Erlang service is what we are working on collaboration with the company Volta Networks. This will be mostly open source. And in addition, we are creating and converting to library as the PCEP protocol I showed earlier for Yang, NetConf, RESTconf, ISAS, all this protocol I've been talking about. We will either create new library for it or get involved in the actual libraries that already exist. So as a segue to the question and answer session, I'll start asking Pierre some questions about the future of the TeraFlow project. So Pierre, do you hear me?
Yes, hello.
Yes. So as a starter, I think that maybe one of the most interesting questions and probably that everybody is thinking about is how we could actually scale in a smart way for this amount of flow. So what's your point on that for the future of TeraFlow?
Yeah. I mean, that's almost multiple questions. So the thing is, for one thing, you have to kind of like scale the infrastructure that you can actually do the general scalability thing, where we probably just have the right tool for that with Erlang, so everything is fine already, and we will probably manage that quite well to actually scale up just horizontally or vertically. One way that the project already looks at scaling is this network slicing, because not only is this a way to kind of like sell off parts of the network infrastructure to other providers and service providers that then do something of their own inside their slice of the network, but you can also do a divide and conquer. But I think the more important thing is that this whole thing is getting much too large to actually understand by human. So nobody can actually manage this manually anymore. We would just run out of humans to actually manage things like this. So the core needs to be automation and intelligence. And the kind of intelligence that we need there is probably not the traditional machine learning one. I mean, it can be part of it, but more like the classical AI with like combinatorial search, heuristic search, and implement these in a distributed way. And I think Erlang has actually something to offer in this space. And it's an interesting space because it's very neglected by far. Everybody is doing deep learning nowadays, and everybody forgot about the traditional AI stuff of combinatorial search, planning algorithms, and of course not the researchers there that are doing the research. But what basically happened in machine learning, we have 1,000 times more compute power and 1,000 times more data than in the 80s, and we are still using the same algorithms roughly. I mean, like tweaked algorithms. I'm sorry, tweaked algorithms that just work better because we have just more compute power. But my question is like, what actually happens with this other AI stuff if we throw more compute power at it? And I think TeraFlow is an excellent project to actually try this out because we need the scalability and we also will get the compute power. And that will be basically like Erlang, distributed Erlang systems with billions of processes doing distributed AI algorithms, like classical AI algorithms, not deep learning, maybe mixed with deep learning, but that's kind of like a thing that will actually be very good for Erlang. So yes,
Yeah.
And we have one more question, I think. We don't have too much time.
There's a question, yes.
Okay. Should I read?
I can read it. I have it open.
Okay, please.
How is this related to earlier flow forwarding link project, like link switch? There was a open flow based project, and I think Sebastian will be the one that can answer this directly.
So as I understand, because I couldn't really open the website for this project, as I understand it is implementation of OpenFlow, notably like router for testing OpenFlow router in Erlang. But what we are doing is really on top of that, we actually could use OpenFlow as part of our system. This is more about managing a network and the interaction between networks, so we can have a configuration spanning a whole set of network from endpoint to endpoint. So this no compatibility. This could be completely use OpenFlow. There's no such thing. This is not the same position in the research. I don't know if this was clear enough. I think I talked a bit about OpenFlow, so to say that it wasn't absolutely incompatible in any way.
Yeah, we would be looking more upwards, basically towards the kind of like general control of the whole thing than the forwarding plane.
So is there more questions? Oh, I see there's one more question.
There's one more.
Yeah,
you see, yeah.
I let you respond.
Well, the thing is, we are an Erlang company, so why would we not choose the Erlang for that? Is the question for us. So we got part of the project, and we naturally pick Erlang for actually implementing these things. And it's actually, I mean, this is basically Erlang yet one more way again where Erlang goes back into telecommunications. I mean, it's coming from telecommunication. It was made for this, and this is kind of like one more application and one more research area to actually bring it back to. I mean, it is still in telecommunications, but it's kind of like one more way to actually apply it to, because it's a natural fit. We have scalability. Having lots of processes is good. Implementing protocols is super nice in Erlang. Once you're used to Erlang, you will hate implementing protocols in all other languages, basically. because it's like, oh, I'm missing everything basically. So it's a perfect fit, but also kind of like it's a natural fit for us as a company.
All right. So any other questions? I have not found any on the Fuba, so maybe I can ask one question. What is the performance goal of the performance you're going to achieve with this TeraFlow? Maybe it will bandwidth, or how many flows, or any kind of quantitative goal you have?
The number of flows it is. Yeah, sorry.
Yeah. So, I mean, one of the goal is kind of in the name of the research group, because the idea is to support a tera of concurrent flows. So this is one of the big goal of it. This is the research is based of the service is to be able to really scale to this number of flows, and network slicing is one of the big optimization. First big optimization, and the second big optimization is distributing this computation algorithm. That is what Pierre was talking about just before. So besides these goals, besides the standard response time goals, and there's no like very strong goals besides the amount of flow that we want to be able to support, and the fact that it has to be stable and support and not crash.
Okay, so right. Okay. Any other questions? Maybe we are. We still have 1 minute. Any other question? Right, there's a question. Well, what about multicast? From Jacob. Any other any comments on that about handling the multicast of this infrastructure you're proposing?
About multicast and transport traffic engineering. I think there's extension for PCEP to support multicast through. I mean, I didn't go far on this because it wasn't really the use case we had, at least for now. But yeah, PCEP is a very used standard to be able to set up traffic engineering flows, and there's extension for everything you can think about. Even so, they are still drafts. You can find anything. So I can't really respond on that in a clear way. But to get more information on that, I would do a search on PCEP multicast and see how this would be supported by the protocol.
I think basically, of course, like inside a network slice, you can do what you want, but I think the focus is mainly on having secure tunnels from end to end, which don't kind of like cross wires with other secure tunnels. So not that the cars of one car manufacturer show up in the network of the other car manufacturer.
Okay. Now we are we've already out of time, so I'd appreciate if Pierre and Sebastian would be able to answer the question on the Fuva question Q&A board. And thank you all for joining the session. And I'd appreciate if you kindly rate the talk in this session and give your comments to the organizer.